It's one of the best-kept secrets of space science. For transporting ambitious and hefty scientific experiments to near space. Though they're not as flashy or headline-grabbing as rockets. For the quickest and most cost-effective trip to near space, they are the time-honored gold standard.
Satellite missions can take 5 to 7 years and millions and millions of dollars to develop, where scientific balloon instruments can be developed on a shorter time frame and much lower cost.
From atmospheric studies to the origins of the universe, they have been the vehicle of choice for some major scientific discoveries. And new superpressure technology, along with sub-arcsecond pointing capability, put scientific balloon performance on par with satellites for certain types of science. An Austrian prince named Victor Hess is a key figure in understanding where scientific balloons have come from and how they're evolving. Hess loved hot air balloons and physics. In the early 20th century, he combined his two passions in making a series of daring high-altitude flights above 17,000 feet. The aim was to measure high-energy particles in the atmosphere. His discovery of cosmic rays landed him the Nobel Prize in Physics in 1936. He was also the pilot of the first scientific balloon. Fast forward to the end of World War II and a man named Otto Winzen. He devised a way of sealing thin polyethylene film with load-bearing tape. His helium-filled balloons made it possible to fly very large and heavy payloads.
He got a patent on that in 1950, and those early balloons were so large they didn't have any way to launch them, except they actually launched them from aircraft carriers.
Modern scientific ballooning was born. The first spacesuits and other pioneering technologies designed for the space program were flown and tested on high-altitude scientific balloons. With the modern space program now at the forefront, Winzen's balloon became a workhorse for carrying large scientific payloads to the edge of space. These balloon-based experiments began to train generations of young scientists. And unlike orbital, satellite-based missions, balloon-borne scientific payloads can be recovered and flown again. No organization launches more scientific balloons than NASA's Columbia Scientific Balloon Facility in Palestine, Texas. Managed by Orbital ATK for the NASA Balloon Program Office, headquartered at Wallops Flight Facility. Since 1963, CSBF has launched more than 2,600 balloons from locations all over the globe for NASA research centers, universities, and international science groups. The scientific balloons they use are made of a super thin polyethylene film that is 0.02 centimeters thick. They can fly payloads that weigh up to 8,000 pounds, 130,000 feet high, to an invisible ceiling where the atmosphere ends and space begins. Due to the natural difference in density between the helium gas used to fill them and the air, they expand to volumes of up to 40 million cubic feet. That's large enough to fit a football stadium inside. From places like New Mexico, Arctic Sweden, and New Zealand, to the coldest and driest continent on Earth, Antarctica. CSBF launches 10 to 15 balloons a year over 4 to 5 campaigns.
When the scientific team comes to the field for a balloon campaign, they will be reassembling their instrument and getting it aligned or calibrated so that it's ready for flight.
CSBF provides and integrates telemetry and command, balloon control, and ballast systems for each science payload.
So the idea is they come, they put their system together, we do a compatibility test to make sure that our electronic systems there's no interference between the science systems and our control systems.
CSBF uses 2 types of telemetry.
The first one is line of sight telemetry, which is sending the data through a line of sight link, which means the ground station can actually see the payload through an RF link. And the second means of getting data from the payload is through over-the-horizon links, which means that the payload doesn't have a direct line of sight back to the ground station, and it utilizes a satellite link to route the data through the satellite, back through another ground station, probably through the internet back to CSBF, where we then deliver it to the science group. And right now, CSBF is supporting up to almost 3 megabits of data, which is 3 million bits in 1 second.
Science will never be happy. They always want more data. They always want more hardware, more storage. So anytime we can incorporate those things, we're always looking at new technologies that we can incorporate into the balloon systems.
With the compatibility check complete, the payload is declared flight ready. The common factor between Victor Hess's hot air balloon flights and the helium-filled unmanned scientific balloons that CSBF launches is that they are both zero-pressure balloons. And an inherent limitation of the zero-pressure design is day-to-night altitude fluctuation.
During the day, the sun heats it up, the gas inside heats up, blows out the vents. Then as the sun goes down, well, then the gas shrivels up. As the gas shrivels up, so the balloon does, you're not displacing as much volume, the balloon starts to sink, and now you're sort of shoveling off ballast in order to stay afloat.
You could lose tens of thousands of feet of altitude. You might fly at 120,000 feet during the day and 90,000 feet at night, which limits the amount of science returned for some science.
Because of this altitude fluctuation with zero-pressure balloons, polar locales like Antarctica and Arctic Sweden, with 24-hour-a-day midnight summer sun, are hotspots for long-duration scientific ballooning. This altitude fluctuation is also the genesis for NASA's newly developed super pressure balloon.
The reason for superpressure ballooning is they have absolutely stable altitude, day-night, and it doesn't matter how cold the atmosphere is. They are sealed.
So your shape is always the same, you always displace the same amount of air, and therefore you have the same amount of buoyancy all the time.
This day-to-night altitude stability allows superpressure balloons and the science they carry to move away from the poles, offering scientists new views of space from mid-latitude locations, like Wanaka, New Zealand, the NASA balloon program's newest base of operation. Another exciting example of how scientific balloons have evolved as a next-generation science platform is the development of the Wallops Arc-Second Pointer, or WASP.
It's a pointing system that we use for science instruments that need to finely point at an object in space. We have a traditional rotator that can point a gondola within 1 or 2 degrees. But there's some science investigations that need to look at an object very, very closely. And so that's where you can get an even closer look to the arc-second level using a WASP system.
When it comes to launching a scientific balloon, all responsibility for the payload, rigging of the flight line, and the launch itself belongs to the Columbia Scientific Balloon Facility. Whether a super or zero pressure balloon that is being launched from New Mexico or Antarctica, the rigging of the flight line is essentially the same. It begins with the payload, where suspension cables connect up to a truck plate, allowing the gondola to hang from the launch vehicle.
And then above that, you'll have our ladder. And the ladder is steel cables that are separated by a foot or two that drape over the launch vehicle, and then they connect to the base of a parachute.
This connection is the parachute separator, which separates parachute and payload after landing. The top of the parachute connects to the base of the balloon.
And at that point, you have our terminate system that has all the control functions for separating the parachute and gondola from the balloon when it's time to terminate the flight.
Parachutes range from 46.5 to 159 feet in diameter, and from 200 to 750 pounds. The bigger the payload, the bigger the parachute. The same can be said for balloons. On the small side,
you have a 4 million cubic foot balloon, and we fly up to a 39 million cubic foot balloon. On a smaller balloon, inflation takes anywhere average around 20 minutes. Then we have the larger balloon, the inflation actually can take up to like an hour and 15 minutes.
Weather is involved in just about every aspect of scientific ballooning.
And weather conditions for launching a scientific balloon must be nearly perfect too. A standard zero pressure balloon calls for winds on the ground to be less than 6 to 8 knots. Low level winds at 800 to 1,000 feet need to be within 10 to 12 knots. On top of that, the surface and low level winds must be lined up in the same direction.
What we can't have is a wind that is opposing. In other words, if
After roughly 2 hours of float time, balloon and payload arrive at the edge of space, anywhere from 110 to 130,000 feet above Earth. Once in clear conditions, a balloon was spotted 260 miles away. Science missions can range from 2 hours to 100 days. When science goals are accomplished, the CSBF crew begins the process of terminating the flight.
We typically file what we call a prior to descent notice with the FAA, kind of let them know that we're thinking about terminating in about an hour prior to a certain specified time.
This is choreographed with NASA's safety analysis data that shows the crew where the balloon and payload can safely be brought back to Earth. When safety criteria is met, a telemetry command is sent, firing an explosive squib that separates parachute and balloon. It also triggers a tear in the balloon, releasing the helium gas. In 50 minutes to an hour, balloon and payload are safely back on the ground.
So we recover both items because we don't want to leave a footprint of NASA having been there. We take everything that we drop in out. It's important from the science perspective also that they can refurbish and refly the instrument many times in some cases. So scientific balloons are being looked at more and more in technology development. We did the low-density supersonic decelerator, or LDSD, testing up for the supersonic parachutes for Mars. I see in the future additional tests that could be done using the stratospheric balloon as a platform to either lift another vehicle, do drop tests. The possibilities are endless.
There are still compelling science questions which can be answered on balloon platforms, and since balloon platforms are the most cost-effective way of going after these really important science questions, that's the way we should do it.
But the superpressure balloon, if you do a 100-day flight, which is what our ambition is for a superpressure balloon, it's space mission science. It's 100 days at that altitude. It's 100 days in space.
Balloons are a stepping stone to space. So this is our growth system for future brilliant people and future brilliant projects.
The scientific ballooning program offers the opportunity to get new technology to space faster than we could ever do with a rocket program to send things to orbit. What the new scientific ballooning capabilities are offering us is a technology. The need is there's lots of great science to be done that we can do on these platforms at lower cost and get the important training to be able to test out instruments. And so now we've met a need with a technology, and that's real innovation.